Hello! Today we're going to explore a fascinating question inspired by a common phenomenon. We all know that when a jet breaks the sound barrier, it creates a massive sonic boom. So what happens when you break the light barrier? Is there a light boom? Does matter, like a spaceship and its crew, transform into light? It's a great question that pushes us to the edge of physics. In this video, we'll tackle this head-on. By the end, you'll be able to explain what causes a sonic boom, understand why the speed of light is considered a universal speed limit, and use a key equation from special relativity to see why objects with mass can't reach it. Let's start with the sound barrier. Imagine an object, like a plane, that is stationary. It emits sound waves that travel outwards in all directions at the speed of sound, like ripples in a pond. You can see here the waves are spreading out evenly from the source. Now, what if the plane starts moving, but slower than the speed of sound? The plane starts to catch up with the sound waves it's creating in front of it. Notice how the waves bunch up, or compress, in the direction of travel. This is why a siren sounds higher pitched as it comes towards you. That's the Doppler effect. But what happens when the plane's speed matches, and then exceeds, the speed of sound? The plane is now outrunning its own sound. The wave fronts can no longer get ahead of the plane. They pile up and merge into a single, highly compressed shock wave. This shock wave, a cone of pressurized air, is what we hear on the ground as a sonic boom. So a sonic boom is the result of constructive interference of sound waves from an object moving faster than sound. So it's natural to ask, can we apply the same logic to light? If we travel faster than light, do the light waves we emit pile up into a light boom? This is where things get really interesting, because light behaves very differently from sound. In the early 20th century, Albert Einstein's theory of special relativity changed everything. One of the core principles, or postulates of his theory, is that the speed of light in a vacuum is constant. It's always the same, for everyone, no matter how fast they are moving. This is completely different from sound, where your speed relative to the wave matters. Think about that. If you're in a spaceship traveling at 99% the speed of light, and you turn on a flashlight, you won't measure the light beam moving away from you at just 1% the speed of light. You'll measure it moving away at 100% the speed of light. Someone watching you from Earth would also measure that same beam of light moving at the full speed of light. This simple fact has profound consequences. To understand these consequences, we need to look at the math. The key equation is for something called the Lorentz factor, usually represented by the Greek letter gamma. The Lorentz factor is calculated as 1 divided by the square root of 1, minus the ratio of the object's velocity squared to the speed of light squared. Here, v is your velocity, and c is the speed of light. This factor, gamma, tells us how much things like time, length, and mass are altered by motion. Let's see what happens to gamma as your velocity, v, gets closer and closer to the speed of light, c. When you're standing still, v is 0, so gamma is 1. Nothing strange happens. But as your velocity v approaches the speed of light c, the fraction v squared over c squared gets closer to 1. That means the term inside the square root, 1 minus that fraction, gets closer and closer to 0. Dividing by a number that's almost 0 gives you an enormous result. As versus gets infinitesimally close to c, the Lorentz factor, gamma, shoots up towards infinity. So what does this infinitely large gamma mean? It means that the universe itself appears to warp around a near-light-speed object. One of the most famous consequences is related to energy. Einstein gave us the most famous equation in physics, E equals mc squared, but that's actually a simplified version for an object at rest. The full equation for the total energy of a moving object is E equals gamma times the rest mass times c squared. Here, naught is the object's rest mass, its mass when it's not moving. This equation tells us the total energy an object has due to both its mass and its motion. Now let's connect this back to our graph. As your velocity v approaches the speed of light c, we saw that the Lorentz factor, gamma, approaches infinity. If gamma becomes infinite, what happens to the energy E? It also becomes infinite. This means it would take an infinite amount of energy to accelerate any object with mass to the speed of light. So let's return to our original question. What happens when you break the light barrier? Based on the physics of special relativity, the answer is you can't. For any object that has mass, a spaceship, a person, a single atom, it would require an infinite amount of energy to reach the speed of light, let alone surpass it. The universe has a built-in speed limit. So there is no light boom analogous to a sonic boom, because the conditions to create one can never be met by matter. Your spaceship and your body wouldn't transform into light. Instead, the energy required to push you faster would increase without limit, preventing you from ever reaching that final destination, the speed of light. Today, we've seen how a sonic boom is a physical pileup of sound waves. We then learned that light is different. Its speed is constant. Finally, using the Lorentz factor and the relativistic energy equation, we demonstrated that accelerating mass to the speed of light is an impossibility in our universe. It's a fascinating example of how mathematics reveals the fundamental rules of reality.